Okay, so if we're going to solve a related rates application problem, we should have a strategy that we're always going to follow. And so I'm going to use this example right here to help me get an idea of what it is that I want to know. So, all right, what do I do? First thing I should do is draw a figure and label any of the quantities that vary. And I say any of the quantities that vary with, you want to use, pardon me, here we go, that vary, you use a variable to label those things that are going to change, right? Some quantities will not change, right? But others will. In this example right here, let's talk about this. A man is walking on a city block by a woman at a bus stop, and she's across the street from him. The two people are 10 meters apart when they're across the street. The man walks due north at 1.3 meters per second. Find the rate of change of the distance between them after 1 minute of walking. So, all right, what's changing? Well, we know that the distance directly from the woman across the street, that's not going to change. That is going to stay 10 meters, right? But what is changing? Well, this distance that this man is walking, let's go ahead, let's call that x, right? That distance x that the man is walking is changing. So we mark that with a variable. And of course, the distance between the woman and the man as he walks along, that distance is also going to change as he moves along, right? He's getting further away. So the next thing is we want to find an equation that relates the quantity with an unknown rate of change to the quantities of the rate that are known. Okay, so what do we know? Well, okay, we might note that this is in fact a right triangle situation. And in a right triangle like this, of course, our Pythagorean theorem applies. And we could say that a relationship between x and h applies, right? And so we could say that, well, x squared plus 10 squared, right? Those are the two legs of our right triangle right here, would be equal to h squared. You can pretty much see that that's what's happening right here. So that is our relationship. So now the next question might be, well, what are we looking for? Well, we're told, right, we want find the equation relating the quantity with an unknown rate of change. So we need something about these rate of change for the quantities whose rates of change are known. So what do we know? Well, this man is walking along at 1.3 meters per second. So this guy's, he's walking along at 1.3 meters per second. When that is our rate, that is what we're going to call dx dt, right? So dx dt we're saying is 1.3 meters per second in this particular case. Now, the other one that's changing, of course, is h. And we're saying we are interested in finding the rate of change of the distance between them. So we want to find dh dt. Right, so we're interested in finding out, well, what is the rate at which these two distance is going to change over time? Well, now we know that, okay, we're given dx dt, we want to find dh dt, so that means that in this case now we're going to have to go through and differentiate both sides of the equation with respect to time and solve for the derivative that will give us that unknown rate of change. Well, let's see what's going to happen right here. If we take the derivative with respect to time of both sides of this equation, we've got the derivative of x squared plus 100, right, 10 squared, is equal to the derivative with respect to time of h squared. Taking our differentiation right here, we know that using our chain rule, we're going to get 2x times dx dt on the left plus 0, right, because the derivative of that distance right here, that never changes, right? That's a nice constant, is going to equal to 2h times dh dt. And so we have our relationship right here. As a matter of fact, we could even say that if we were to do a little bit of algebra right here, that 0 goes away. And if we took x divided by h, whatever those two distances are, times the the rate of change in x with respect to time, we'll be able to find dh dt, right? The rate of change of the distance between the two people. Okay, so what do? Well, we actually need to have an x and we actually need to have an h. And that was the other reason that we were given this other bit of information right here, right? We were told we want to find the distance between them after exactly 1 minute of walking. Well, we're going to have to do a little bit of extra math right here. How far has he actually moved? Well, if he's moving at 1.3 meters per second, that means he's moved for 60 seconds, right? So that means that the distance x at this particular point in time is going to be 1.3 meters per second times 60 seconds. Right? So this is the point where you can get out your calculator if you like and do this multiplication right here, 1.3 times 6, and you find that this guy has moved 78 meters distance, right? How about h? Well, this is where we're going to need this relationship right here, right? So now if we want to figure out what that distance is, well, 78 squared plus 100 is going to equal h squared. So we're going to have to add these guys up. 78 squared plus 100 is 6184. So we're going to take our square root on both sides, and we only need the positive value of this one. So the square root of 6184 will be h, and that square root is going to be 78.6 meters. All right, so this is where we're going to make our substitution. We're saying 78 divided by 78.6 times the rate of change, which we know is to be 1.3, will give us that dH dt. So now again, using our handy dandy calculator right here, take 78 divided by 78.6, multiply that result times 1.3, and you find 1.29 as the rate of change h with respect to time, and that's what we were looking for. And so we're done.